addressing innovation in catalysis as a tool for greener chemical products. Professor G.D. Yadav earned his chemical engineering degree in 1974 and his PhD in chemical engineering in 1980 from ICT. He is also the chief coordinator of the Center for Nanosciences and Nanotechnology and Center for Green Technology of the University of Mumbai at Kalina campus. Earlier, Dr. Yadav was Darbin Seth Professor and Head of Department of Chemical Engineering, as well as Dean, Research Consultancy and Resource Mobilization at ICT. He's made seminal and extensive contributions to green chemistry and technology, catalytic science and engineering, phase transfer catalysis, nanomaterials, nanocatalysts, and biocatalysis. He is honored by a number of fellowships and awards, including Fellowship of INSA, Institution of Chemical Engineers in the UK, among others. He is an active consultant to a number of industries, and his research is commercialized. He has published 219 original research papers in 41 different international peer-reviewed journals with high impact factors, which find over 2,500 citations in papers with an H index of 25. He's got 27 books and monographs and international company brochures. He has 3. He has obtained 31 patents and developed a UDCAT series of novel catalytic materials. He's guided 55 PhD students in chemical engineering, technology, biotechnology, and chemistry, and 52 master's theses as a single guide, written 2 books. He has currently 15 PhD and 8 master's students under his supervision. He's clearly a very busy person. And he is associated with a number of central government committees like the CSIR, the DST, the DBT, the UGC, the AICTE, and other professional bodies. Thank you very much for joining us today.
Thank you. Yeah. Good evening to all of you. I'm indeed delighted to be here, particularly post tea session, because everybody's awake, you know. Otherwise, after lunch, people go to, in trance. What I'm going to do is glance through some of the work which we have done, particularly with reference to new type of catalysts and processes, with green chemistry and green engineering as the theme. So the most important part of our research has been the enhancement of rates of reactions and selectivities of single phase or multi-phase reactions. Here, we could have, without any catalyst, we can have a nanomaterial in the reaction phase and still increase the rates of reactions and get the desired selectivity, provided we have the material as a nanomaterial or a nano droplet, okay? So this could be a very interesting aspect. Then of course, catalysis is well known to all of you, and the catalysis in synergism with the different modes of energies like microwaves. So first I will start with a very interesting aspect, which is a practical relevance, that is multi-phase reactions, where we deliberately impose mass transfer resistance on a chemical reaction, which normally people won't do, and they would like to have a homogeneous reaction. So I can give you one example: gas, liquid, solid reactions, or you may have 4 phases: gas, 2 liquid, and solid reactions. And here I will show you the role of nanophases in process intensification. So here they may be nanoparticles, they could be inert particles, they could be catalysts, they could be generated in situ, and they will have a very large role in intensification of reactions. So we can convert a single phase reaction into a 2-phase reaction, 2-phase reaction into a 3-phase reaction, and 3-phase reaction into a 4-phase reaction, and we'll look at the beauty and charm of some of these reactions. Well, the textbook says that if you absorb chlorine in caustic, you will get sodium hypochlorite and sodium chloride. Now here is a classic example that if you have this is a so-called instantaneous reaction, gas-liquid reaction. So if you create next to the gas-liquid interface, as I show here, that this is the gas-liquid interface, if I create 2 reaction planes, then on one reaction plane, H4Cl, that is hypochlorous acid, is generated, which in fact reacts with hydroxyl ion, and that is how you get OCl minus, and that is how the bleaching powder which is generated, whether it is the calcium hypochlorite or sodium hypochlorite, then you have a solution where degrades over time. In our experiments, what we showed through theory and experiments, that HOCl can be dissolved from this directly, and if you absorb HOCl again, when react with NaOC, NaOH or calcium hydroxide, you get a bleach which has only hypochlorous ions and no Cl ions, because Cl minus is the one which degrades it. Now the beauty here is, if I have the additional phase, what happens? So if I have additional phase, like in the case of calcium hydroxide, this plane goes next to this gas liquid interface, and therefore the rates of reactions are enhanced by orders of magnitude. At the same time, the selectivity to hypochlorous acid is increased. Nobody would believe that you could dissolve hypochlorous acid from sodium hydroxide solutions. This we published long time ago, and this has been practiced by Dow Chemicals in their Freeport plant. Okay, the other example is benzyl alcohol production by an eco-friendly route. Typically benzyl alcohol will be produced by oxidation of toluene, and you will have a variety of things going directly to benzoic acid. Here in this case, if you take toluene, I know this is only one has been shown here, but this is done under light and UV light, and you can get benzyl chloride as one of the. This is acid hydrolysis, can directly give me benzyl alcohol, and then HCl generated. This is back recycled, converted back into chlorine, and this is used. This becomes a complete cycle. A plant has been erected on the basis of work which we did by Gwalior Chemicals, and this is the world's largest manufacturing unit of benzyl alcohol. Okay, normally people show Sheldon's this famous table where the E factor which is given, but this is not shown. Why the E factor for petroleum refinery is much lower in comparison with pharmaceutical and drugs, and you will see that in this case these processes are continuous processes and they use heterogeneous catalysis. The number of stages are low. So this mode of operation, as you go down, you find that number of stages increase, the role of catalysis decreases, and many types of solvents have been used. And pharmaceutical industry is crazy industry, which uses solvents anywhere between 1 to 10, and they don't know why they are using it. Only thing, they will ask a chemical engineer to distill it up and give the solution back to them. However, you will see that the role of understanding fundamentals of chemistry as well as engineering can certainly help us. So as far as our group is concerned, we have been working in solid acids and superacids, and then solid bases, super bases, redox materials, and supported enzymes. And so the first work which we did, this is a classic paper, citation classic, and sulfated zirconia, then clays, heteropolyacids, zeolites, ion exchange resins, and the so-called UDCAT series of catalysts which we developed in our department, and also mixed oxides. So several novel catalysts were developed, UDCAT 3, 4, because this UDCAT 3 is the redox material, 4 is a mesoporous, UDCAT 5 has got the highest superacidity reported so far in the literature, UDCAT 6 is mesoporous, and again UDCAT 7 is a bifunctional mesoporous. Well, this is well known to everybody what sort of industries are using acid catalysis. I will not go into the detail of this, but you can see that the important thing to be noted here, in comparison with the homogeneous catalyst, is that there are several issues related to homogeneous catalyst, and we look at superacids and hamid acidity. Sulfated zirconia is supposed to be the superacid, having 10,000 times strength. It is stronger than sulfuric acid, which has H minus, H naught minus of about 12. So you can go here. So we targeted this particular area, and we said that the ideal target is the magic acid, which is with minus H minus H naught is 20, which can protonate methane as well, which is very difficult to produce. So one tries to go in this direction, and so we tried to do this, and we focus in this particular area. We studied a variety of different so superacidity of minus 12. So it is dependent on the nature of the acidifying agent, method of acid treatment, precalcination, sulfur content, crystallinity, and nature and strength of acidic. So here in UDCAT series, we prepared the first catalyst which we have patented in 5 different countries. The UDCAT 1, which is a mesoporous, again a solid superacid, And UDCAT2 is a specific safe-sieving catalyst where we can choose the safe-sieving property of this. For example, we did this UDCAT1, which has been used for cracking, nitration, acylation, and alkylation of variety of products. For example, ethyl benzene, ethylation with dilute ethanol. Normally people use ethylene. We have used dilute ethanol to show that it is a very good catalyst. Well, in nitration of chlorobenzene, we could give para to ortho ratio of something like 13.2 to 1 by using this UDCAT2 series. In fact, we could further go to something like 15. Well, this catalyst has also been used for cyclization reactions and nitration reactions. Well, in the case of redox catalysts, particularly oxidation reactions are very difficult to control, and you know that the variety of products, including the danger associated with oxidation reactions. So here we synthesize a manganese vanadium tertiary or ternary oxide with the framework of manganese oxide octahedral molecular sieves. So this is OMS2, and you can see that this particular nanocrystalline redox material was used for a variety of reactions. So typically, TS1 is used as a catalyst with 30% hydrogen peroxide, and you can have hydroxylation reactions, oxidation reactions, and whatnot. And these are the products which have been produced by using this technology of TS1. We did all these reactions, and some of them I'm going to show you. For example, the oxidation of cinnamyl alcohol by using our UDCAT3 catalyst. You can see that this gives a selectivity of 97%, yield of 92%, turnover frequency of 31, our inverse. And again, so you can see that this is a very good catalyst in comparison with TS1 and other reported catalysts. We did hydroxylation of phenol, and you can see again, you get hydroquinone and catechol, and we could get something like 74% of hydroquinone and 26% of catechol. So this is the comparison with literature values. Then hydrogenation was also done by using this UDCAT3, where para-nitroanisole to para-anisodine, and you can see that this catalyst gives 100% conversion and 100% selectivity in comparison with for instance, 5% palladium on carbon. Well, in the case of heteropolyacids and modified catalysts, we synthesize heteropolyacids in nanomaterials inside the pore structure of this acidic K10 bentonite type of clays, rather montmorillonite type clays. And you can see that these type of catalysts have been used, for example, in the synthesis of MTBE, okay, in the synthesis of the so-called Keuda smell, that is phenylethyl alcohol condensation with methanol to get this phenylethyl methyl ether, or for that matter, bisphenol A synthesis by using phenol and acetone. Well, this could also be used for oligomerization of 1-deacene, and once you have this, if you get 100% dimer, this can be further hydrogenated to get the polyalpha olefins PAA. This has been published in Green Chemistry. Well, we could do alkylation of phenol with MTBE or tertiary butanol for that matter, and we can show that these heteropolyacids supported on K10 type of catalysts are very good catalysts. In the case of this biodiesel, trans-esterification of edible and non-edible vegetable oil, but this paper is just published recently. We could do a variety of these reactions by using this heteropolyacid-based catalyst, and we have synthesized the ethyl esters of linoleic acid, then palmitic acid, and stearic acid, and the combination when we use these edible oils and non-edible. Toluene alkylation with methanol has also been done, and this is a very interesting process, again based on heteropolyacids, and you can see that the selectivity is very high in comparison. So this is with dodecatungsto phosphoric acid on clay, gives a very high selectivity on toluene alkylation with methanol. Well, one can also extend this to regioselective reaction and separation based on the CCM substituted heteropolyacids, where xylene, any mixture of xylene could be taken. For example, we can react this with benzoyl chloride to have the acylation reaction. One can go also with benzoic acid or dibenzoyl ether. And for example, if you do this type of reaction, selectively, depending on the catalyst loading temperature and the mode of operation, you could produce one of these selectively. So this we have published in one of the earlier papers here. Well, we could also do diisopropylation of phenol, okay, with the same catalyst. It's a nanocatalyst, and you can see that here we had used the ether, for instance, And also we have done this reaction with isopropanol. So we can get this type of, dialkylated, this is diisopropyl, phenol. This has a lot of interesting applications, including medicine. Then you can further, convert that into hydroxy groups, or you can have acids generated on this. Well, the other interesting aspect is the cascade engineered synthesis. That is, instead of having multiple reactors and separators, you can combine them in a single reactor and separator, and therefore reduce the cost of operation and also the material cost. So I will give you one example, that is the cascade engineered synthesis for bisphenol A, where this bisphenol A has many interesting applications. And the typical process by which phenol is more prepared is called the Hock process, where it is vapor phase isopropylation of benzene to cumene, then auto-oxidation of cumene to cumene hydroperoxide. And this reaction is a highly dangerous reaction, and a lot of accidents have taken place while concentrating CHP. So in the Hock process, again, see, manufacture and our concentration leads to explosion. So what we did, instead of directly reacting phenol with acetone, we thought of another idea, and we did a cascade engineered synthesis. And you can see that with this particular process, we could get very good yields of bisphenol A, and this is given here. This is published recently in OPRD. So we can here see the conversion of cumene hydroperoxide is 75%, selectivity is 100%, and temperature is 40 to 60, so there is no explosion hazard. So this is and then you get atom economy of 100% for this reaction. Well, in novel solid bases, we have developed some new materials, novel synthetic techniques, and again, these are novel. So here we have novel hexagonal mesoporous HMS type of silica, where have the hydrotralsides. And here we have given one example of alkylation of hydroquinone with dimethyl carbonate. You can see that the conversion is about 70%. One can go to higher conversions, but this is just to show you the typical reaction, where selectivity, this monomethyl ether, is something like 76%. While in aldol condensation, the jasmine aldehyde is a very interesting reaction, and this reaction from viewpoint of chemical reaction engineering as well as development of a catalyst. So here what we have done, in this particular case, we have taken this catalyst which we developed, a solid base, and you can see that selectivity jasmine aldehyde something like 86%, conversion of heptanol is 82%, and here we have, so these two reactions are given in this particular case. The same catalyst was used for pseudo-ion synthesis, where with citrol we can get something like conversion of 85%, at 120 series. Aniline and alkylation has also been done by using this same catalyst, and you can get methyl and phenyl carbamate rather in this reaction. A lot of work has been done throughout the world on using vegetable oil to biodiesel and glycerol, and glycerol is supposed to be a byproduct, but typically about 1 kg per 10 kg of this. Now people have been talking about uses of glycerol. Whether one could use to make epichlorohydrin. Earlier epichlorohydrin was used to make glycerol, so it is reversed now. 1,3-propendol or 1,2-propendol, acrylic acid, and 3-hydroxypropionic acid. We have a big program going on in this area with NCL, so for reasons of proprietary I won't tell you, but we have got very exciting results for which patents have been filed. Well, in cascade engineered catalyst, where we can use solid acid, PTC. Now I will give you some example. One interesting example is 1-part synthesis of MIBK using aldol condensation with 3 functions, that is trifunctional catalyst, in hydrogenation, in a cascade, and acetate as a starting reactor. This is a typical reaction, setup, a flow sheet for MIBK synthesis. You can see the number of reactors and separators used in this process. Here is our flow sheet where we have just 2, and how we do that, we try to understand the entire mechanism independently. Okay, starting with isopropanol, okay, and this, you can see that there are basic sites on this catalyst, there are acidic sites on this catalyst, and there are metal centers. So we synthesize this catalyst, this is a nano catalyst, I've given this acronym as a PCH and TI, with magnesium and aluminum and titanium in that, and you can see that this is a very good catalyst which gives us I would not go into the details of the reaction mechanism. We understood the reaction mechanism. On each side, what happens? whether it is aldol condensation or dehydration or and hydrogenation. So there is a sort of interesting cycle going on the catalyst. While hydrogenation of styrene oxide we also studied using this palladium encapsulated palladium. We developed two different type of catalysts, encapsulated catalysts. So we can and we have modeled this reaction, and this is submitted for publication, where you can get 2-phenyl alcohol or 1-phenyl alcohol or phenyl acetaldehyde in this case. Well, we have done this work. Interestingly, supercritical CO2 as a medium is a very interesting medium, and we can do this. Okay, for example, we have this setup where you can see the phases, single phase in two phases, and you can see at what temperature and pressure single phase is obtained. Now, so hydrogenation in supercritical conditions, we have done some reactions, very interesting reactions where, we have filed for patents now where we get, very good selectivity. Well, a lot of people have been talking about reactors and particularly microwave reactors. The problem with the microwave reactions is that there is no consideration for the reaction whether it is heterogeneous or homogeneous. Nobody bothers about the mixing patterns and mass transfer effect, heat transfer effects. And the chemists always like the round bottom flask, which is the worst kind of reactor to be used anytime in your life. So if you look at these microwave reactors, how reliable is the scale-up? Because we can do it as a synthetic tool in the lab, but not really on an industrial scale. So unless it has been made as a continuous process. So a few grams in a few minutes, very good. A few kg per day would be really good for pharmaceutical industry. And if you could do it few tons a day, that will be the icing on the cake. So real issues are in this particular case. Majority of these are multiphase reactions. People do not understand the mixing patterns. They do not understand the mass transfer effects. They do not understand the heat transfer effects, the kinetic parameters, power input per unit volume of the reactants, and the hazard and safety issues related to this. So how does microwave affect the rates and selectivity? Does it affect the rate constant? Does it affect the mass transfer rate or mass transfer coefficient, interfacial area, solubility, adsorption, desorption, or the equilibrium constant, surface properties of the catalyst, effective diffusivity in or distribution coefficients, orders of reactions, droplet size, particle size, and name it. So in the case of phase transfer catalysis, we did some of this, I would not go into the details of the multi-phase catalyst, but how do microwaves or ultrasound affect the rates of phase transfer catalysis and why? So we could do this with ionic liquids. We could do this synergy with microwave, chemical, biochemical, or enzyme catalyst. For example, here is one reaction that suppose you have a phase transfer catalyzed reaction with non-catalyzed reaction. That is given this RAR is a non-catalyzed reaction rate, initial rate of reaction. This is the enhancement factor. You can see that large enhancement factor could be achieved. But if you have alone just microwave reaction with this, and if you have both microwave and the phase transfer catalyzed reaction with reference to a phase transfer catalyzed reaction. So both rate constant and equilibrium constant could be found by the theory which we develop for this particular type of experiments. So we can see that the typical equation where rate constant K is given by pre-exponential factor Arrhenius into e raised to minus EA by RT, and where with the delta G minus RT ln K, you can find that the microwave affects this the pre-exponential factor more than the activation energy. Okay, so that is what happens. So you can get the same activation energy with the microwave as well as with the conventionally heated reactant. So suppose I have a triphasic and biphasic reaction which I was talking about. The rate enhancement by order of magnitude and 100% selectivity can be obtained by converting a two-phase reaction into a three-phase reaction. So how do we do that? You can see here that the middle phase is the catalyst-rich reaction phase, organic phase is on the top, and aqueous phase is on the bottom. So we can have three independent stirrers. There is a trick by which we can do this, and you can see that this is the, when you keep it in a beaker, this is how the three phases are separated. So here we can apply the mass transfer with chemical reaction theory, and we can find out where is the locale of the reaction, whether it is, this is one interface, this is another interface, okay, and this is the middle phase. Does it happen over here or does it happen over here? So this fundamental understanding of diffusivities and equilibrium constants and all that is required. So it can happen on this side or it can happen on this side. Suppose it happens on this side, you get different type of selectivity. Suppose you happen it on this side, you get different type of selectivity. So if you understand that, you can see very high you get. First view is you get, there is a decrease in the activity, and that is because there is some degradation or deactivation of, if you do it in situ conventional, so you see in situ microwave is always greater than the in situ conventional, okay? And the first use, and ex situ conventional and ex situ microwave, you can see this. So interestingly, this type of reactions can be analyzed from fundamental viewpoint. We can find out that the inhibition constant, we can find the rate constant, and ultimately a kinetic model we have developed based on the initial reaction rates, where all these constants have been extracted from the same set of data. So for instance, in the case of synthesis of perlauric acid, we have given this is the Vmax, is the maximum rate of reaction, and this constant, Kma and Kmb are the equilibrium constants. So you can see that in the case of microwaves, and conventional, you can see microwaves are quite high in comparison with conventional, and you see that if you plot this on the same plot, they are almost parallel. That means the activation energy is not changed by micro. It is the pre-exponential factor which is mainly responsible for enhancement in microwave catalyzed reactions. Well, finally, we also have been working in energy engineering, that is hydrogen production and storage. We have a big program in this, where water splitting we have been doing to copper fluorines. I will not talk about this, but so to conclude, green chemistry principles can be adopted for a number of industrial processes. If we understand the basics, we can develop new type of catalysts, we can develop new type of reactors. Converting biphasic reactions into triphasic reactions leads to waste minimization and economic benefits within the realms of green chemistry. And cascading of reactions always leads to better catalyst utilization, reduction in separation cost, and enhanced throughput and economics. So this is my group, okay, which has been working in this area, and I must acknowledge the large number of funding agencies who have been funding my research over these years. Thank you very much.